Okay, I need you guys to turn to page 37 in your notes booklet. We're going to look at radioactive decay rates. Okay, and a decay rate is how fast something decays, right? So that's what I mean by that is like how fast something decays. So, or how fast an isotope decays. Oh, it's challenging. Okay. Here we go. Okay. And each element has a specific and unique decay rate associated with that element, like or associated with that isotope. And that rate isn't affected by things like temperature, pressure, environment, or even the daughter nucleus that comes off of it, right? So you can change the temperature, you can subject it to like a higher or lower temperature or more pressure, and that doesn't affect at all how fast it decays. But there is a probability involved in that decay rate. Okay, so a sample of an isotope of an element contains many atoms and therefore contains many nuclei that are the same. And it's not possible to predict the decay of like a specific nucleus. You can't pick out a nucleus in that sample of the element and say this nucleus will decay at this time. But you can predict the number of nuclei that are going to decay in a given sample over a given time period. So you can't predict the decay of particular nuclei. You can just predict how many over a period of time. And that decay rate, the rate that something decays at, is called half-life. So those of you that have taken the logarithms unit in Math 30 have dealt a little bit with half-lives. We don't have to do logs in Physics 30, though we just do simple decay rates. So half-life is the time it takes half of the parent atoms to transmute into something else, which is then the daughter atoms, the daughter nucleus. And half-life is a time, like another way of saying it, half-life is the time required for 1/2 of the atoms in any sample of an isotope to decay. And this is just a chart from an older physics textbook that I had that has half-lives of common radioactive isotopes. So you can see that there's a vast difference in half-lives here, right? Beryllium-8 and polonium-214 and oxygen-10. The beryllium and the polonium have very, very quick half-lives, right? Especially the beryllium, like times 10 to the negative 16 seconds. That's like the blink of an eye or less than that. Oxygen's a more reasonable time, and then you get up to things like uranium-238, which has a half-life of 4.45 times 10 to the 8 years, right? A means annum, and that's just another way of saying year. Okay. And so what that means in terms of fast or slow decay rate, a fast half-life, so something that decays very fast, means it will disappear. Its radioactivity will disappear very quickly, so it doesn't stay radioactive for long, which tends to make it a bit safer once it's decayed, right? When you're around the decay, that's dangerous. If it's gamma rays that are coming off of it, or even beta that's coming off of it, that would cause some damage. But once it decays, it's no longer radioactive. Whereas when you get down to these things like americium-243 and plutonium-239, uranium-235, uranium-238, they have a ridiculously long half-life, which means they stay radioactive for a long period of time, which means they're always dangerous, right? 4.45 times 10 to the 9 years, like that's over well over a billion years, right? There's a million, billion. Yeah. So that's like well over, like that's basically 4 billion years it takes until that's decayed, which means a couple things. It means you always want to be wearing the proper safety attire when you're exposing yourself to uranium, but it also means that that's one of the reasons why it works really well in a nuclear reactor, because its radioactivity lasts for a long time. Okay, a decay constant is a property of an isotope that gives the probability of any nucleus of that isotope decaying in a specific unit of time. The greater the decay constant, the faster the decay. And then radioactivity, which is also called activity, also called decay rate, as a sample decays, its activity becomes less, or its radioactivity becomes less. So if you go back here to this list, right, like as mentioned there before, like so as beryllium decays, which it decays really fast, the radioactivity left in the sample that you have left of beryllium, it becomes less, right? It's not as harmful. Okay, so as the mass of a sample decreases through radioactive decay, the radioactivity of the sample also decreases. Radioactivity is measured in arbitrary units. Like, we don't have one specific standard international unit to measure it in. It might be decays per second or becquerels or some different units. The decay rate of radioactive isotopes is also, it's not linear, so we would never use a linear graph to describe it. It doesn't look like this. Okay, that doesn't work. And red. Okay, so we'll cross that out. So it's not linear. Okay. Oh, I probably lost the. Yeah, I lost the thickness of my pen a bit. Oh well, maybe it's easier to write in the thick one. We'll stick with the thick for a while. So it's an exponential function. So you get like an exponential graph. So if I try to draw a graph like that, where we would have time on the bottom on here, and time could be in seconds, it can be in days, it can be in years. It depends on the decay, like on the sample and what its decay rate is. And generally, what we tend to have on the y-axis is percent, okay, or percent remaining. I'm gonna do this differently here. So I'll do this as percent remaining. It's just easier to type it. Okay, so percent remaining, and that's what usually goes on here. So what that means is that we usually have, let's see if I can get the text again. So if I draw a text box here, right, like at the top, this would be 100%, and then down here at the middle would be 50% left, and then down at the bottom, right, it would be, like right at the bottom here would be 0% left, and then in the middle you'd have like here, approximately the middle. That doesn't quite look like the middle because of what I've done here. In terms of typing, you'd have 75 in there. Yeah, I don't think I can do anything. Anyway, and then over here, well, so let's actually move this down a bit there. So it's 50, 75, and then this would be 25, and so on, something like that. You know, it's not exact there because of the way I've typed, but that's okay. So that's what that would be. And then the way that the curve would look is it sort of starts at 100, right? And then it works its way down over time. It kind of falls like that in a much more smooth curved line. But anyway, I should have made a, actually here, just give me a second. I'm going to pause this. Well, to you it won't look like I paused it, but I am going to pause it. Let's see if this works here, actually. This might just be a little bit better. Ah, there we go. Okay, so I'll just make it smaller. So I copied the graphs that I had in my notes already because I thought it just was a little bit nicer. So there we go. So let's just use that instead because it's drawn a little bit. Oh, it's drawn a little bit better. Sorry, somehow the back of my screen disappeared there, and I was just trying to get rid of this. No, we'll ignore that. We'll just make this. We'll cover it with stuff. Like that. So what I was trying to get at here was that you know, we have there's our time, and in this one I've got it labeled as days. And again here I've got percentage of sample remaining, so 100%, 75%, 50%, 25%. So of course, if you start with a sample, you're going to start with 100%, and then you have some of it disappearing over time. And what this actually shows, this shows the half-life, you know, very well, because this is one half-life here. Okay, so that would be one half-life, because you go from 100 to 50%, so half the material is gone. This would be two half-lives, because then you're going from 50 to 25. This down here would be three half-lives, because then you're going from 25 down to 12, 12.5. and then, you know, you've got like 6.25, so that would be your fourth half-life, and then it keeps going. And the thing about half-life and about radioactive decay is you never actually run out of the sample, right? There's always a smaller amount to have. You can always go smaller and smaller and smaller. So that's one type of graph. That's percent versus time. Then this one, which isn't labeled, so now I'm back into having to write with this pen here. So this is radioactivity versus time, which I will just short form radio versus time, but that should be radioactivity versus time. So what this does here is this is showing radioactivity over here. So this is showing like how radioactive it is. And you're starting with like a radioactivity of 40, whatever the units are, and then over time. So then of course 20 would be your first half-life, right? Because that's half the radioactivity left. Then 10, right? That is not drawn so well. Then 5, and so on. This could also be mass. Right? You could have mass, and then if you want to know the half-life in terms of mass, you look for how much mass did you start with, and then the first half-life would be where the next mass is. And graphing, it's a good way to kind of confirm. Well, like when you graph an actual thing, and you guys are going to try this on Thursday, when you actually do a graph of radioactive decay, we're not going to use real decay, we're going to use candy, because it can't use actually something that's radioactive. You find that the half-lives aren't exact, right? Because there's a probability involved in it, the half-lives aren't exact. And so then that's kind of a bit of an issue, but that also shows you the statistical nature of it, and that it's not an easy thing to predict. Okay, so now to a couple different types of calculations that you have to deal with half-life. And so the stuff that you have to do is going to be quite simple. Like I said, no logarithms. So when you solve for an exponent, it's going to be an easy thing to solve for. You won't be solving for like a part of an exponent. And this is an example here. Thorium-234 has a half-life of 24 days. So if you begin with 20 grams, show how much is left after heat, 3 half-lives. So you just take 20 and divide it by 2. Okay, so then that gives you 10 is what you're left with. And then you're going to divide it by 2. And then you're left with 5 grams. Okay, which you will, let's see, this is 1 half-life. This is 2 half-lives. So we still need another one. So you have to divide that 5 by 2, because that's our 3 half-lives. Okay, so then that means there's 2.5 grams left after 3 half-lives. And 3 half-lives, right, this is 24 days. Plus another 24 days. Plus another 24 days. Right, so 3 half-lives. That equals 3 times 24. Or 2.5 grams left after 72 hours, or 72 days. Okay. So that's a rather simple calculation. Look at that one. And this is another version of the same kind of question, just asked a little differently. Tritium, which is hydrogen-3, it has a half-life of 12.3 atoms. That means 12.3 years. That atom means years. How much time is required for its radioactivity to reach 1/4 of its original value? So 1/4, if you take 1 and divide that by 2, right, that gives you 1/2. That seems pretty obvious. Okay. Oops, I didn't, yeah, I did the divide by 2. Okay, so then 1/2 divided by 2, which with fractions is 1/2 times 1/2. That leaves you with 1/4, right? So it's 2 half-lives. Oops, that should be a 4. Okay, there. Tell me which one. So that would be 4. Holy Hannah, what's going on here? There we go. Okay, so that would be 1/4. So this is 2 half-lives. 2 half-lives until 1/4 is left, and so then that's 2 times 12.3 years. So that gives us 24.6 years. till a quarter is left. You know, if it asked until 1/8, that's 3 half-lives, you know, 1/16, that's 4 half-lives, and so on. You're just constantly dividing by 2. Okay, now there is actually a formula for this, and the formula for half-life is, let's see if I can draw this nicely on here, n, which is the amount after n half-lives, so that's the amount after n half-lives, or the activity, or the percent, right? This could also be percent left. Oh geez, that got squishy. So n is equal to n naught, okay, so NO, which is your original amount, or your original activity, or if you're talking about percent, always, if you're talking about percent, that'll be 100%. And then this is bracket 1/2 bracket to the power of little n. Okay, so that's your formula for half-life. That's what's on your formula sheet. What you actually have to remember is what that n stands for. So here we go. N is number of half-lives, or time over half-life. T over T1/2. So really what this formula becomes most of the time you use it is n is equal to n naught times 1/2 to the power of, I'm writing calculator steps in here, and you want to make sure you have a bracket here, time, which is the total time, the time that you want to know what's going to be left after, divided by half-life. And that half-life, the symbol is T with a little subscript of 1/2. Okay, so that's what you actually need to use. And you need to be really careful in your calculator. Remember that bed mass, and so in bed mass, you need to find, you need to do this part first. You do 1/2 to the power of T divided by half-life, then you multiply by n naught. Okay, there's a real tendency to take this number, multiply it 1/2, and then raise it to that power, and that's not what you do, right? Bed mass says you do brackets first, what's in brackets, then your exponents next. Okay, so let's try, I'm going to go to purple. So let's try a few examples using this formula. Thorium-234 has a half-life of 24 days. If we start with a 20-gram sample, how much thorium is going to remain after 10 half-lives have passed? So this is 10 half-lives, that's your N, right? Because what that means is that time divided by half-lives is 10. Okay, so it's a whole number of half-lives there. So N equals N naught times 1/2. Okay, and this is one that you can do to the power of n, and you can do it this way. So we start with 20 grams, okay, and you can use any units in the half-life formula, because this isn't really a standard international formula at all. The only thing you have to be careful of is that your time and T1/2 are in the same unit. So 1/2 to the power of 10. So in your calculator, you're going to do this part first, 1/2 to the power of 10. And if you actually just type in 20 times 0.5 to the power of 10, you're going to get the right answer. Okay, so if you just type it in that way straight across, just type it in as you see it, you're going to be okay. It's when you start to break it down and do it in steps actually where you end up kind of going wrong. So 20 times 1/2 to the power of 10, doing the 1/2 to the power of 10 first, and then times 20, is going to give you 0.0195 grams left. It's hard to tell, but that is a 9 there. Okay, fixed up a bit. Okay, so that's an easy part of the formula to use. That's just using the formula as it is on the formula sheet. It's when you're given a time that doesn't give you a whole number of half-lives, right? Because 60 divided by 24 is going to be like 2 point something. It's not an exact number. That's then when you end up having to go back and use this expression for n. Whoops, I covered that up. Okay, so how much thorium-234 remains after 60 days? So again, here's our formula. N equals N naught times 1/2 to the power of T over T 1/2. And you know, if you're really worried about the calculator, find what that is first, right? Like actually go 60 divided by 24, because that's what N equals, right? N is equal to that, which is time over half-life. Ooh, that got really bad. That didn't look good at all. Anyway, okay, so we have 20 grams times 1/2 to the power of, and that little caret is what you have to use on your calculator, to the power of bracket 60 over 24. And you should get, for this one, 3.54 grams. Which makes sense that it should be more than what was left up here, because this was 10 half-lives, and this is about two and a little bit half-lives, 2.5 or so. And, you know, try that on your calculator a few times just to make sure that you can get it, and make note of it if you're having trouble on your calculator, and I'll help you with that on Wednesday. Then when does the mass of thorium-234 reach 1.25 grams? So this one you don't have to do logs. I can show you logs, or we can do an example using logs, because you can use logs to find this. But really, whenever you're asked to find when does, you're basically looking at how many half-lives. And it will always be a whole number of half-lives. And all that you do is just start with your initial amount, which is 20, and just keep dividing by 2 until you get to 125. So 20 divided by 2 is 10, divided by 2 is 5, divided by 2, oh, Jesus, okay. I'm going to start over, that looks pretty bad. Let's just try that again. I'll go a little bit slower. I was getting speedy and thought I could do a better job. Okay, 20 divided by 2 is 10, divided by 2 is 5, divided by 2 is 2.5, divided by 2 is 1.25. Okay, so then we look, and we've got 1, 2, 3, 4 half-lives. So 4 half-lives is equal to 4 times 24, which I believe should be 92. Oh, 496. Sorry. So 96 is it days? Days. Now, of course, you can use logs, and that would be really hard for me to do on the just using my mouse here. So I'll do it on the board for those of you that are interested on Wednesday. Okay, so we'll try an example using just a different NO, a different type of NO, which is just activity in becquerels instead of just these grams and things like that. And the one type of example that I didn't do on here is percent. So we'll make sure to do some percent questions in your workbook on Wednesday. So the activity of a sample of lead-212 is 3.75 times 10 to the 8 becquerels. Okay, so that's your NO. Its half-life is 10.6 hours, so that's half-life. And we want to know what will the activity be, so that's N, that's what we're looking for, after 1 day. So now here, it doesn't matter units, but these need to be consistent. So we need to write that time in hours. And so 1 day is 24 hours. Okay, so N equals NO times 1/2 to the power of T over T 1/2. So now we've got a lot of writing to do here. Okay, so that is 3.75 times 8 to the power of 8 becquerels. And that's just an arbitrary unit. The units actually don't really matter, and that's all one number, so be careful about that. Then it's times 1/2 to the power of 24 over 10.6. Okay, and that's in brackets there too. And so you should get, so that's roughly, you know, two and a little bit half-lives. So 7.81 times 10 to the 7 becquerels. Good. Okay, and the last example is one that uses a graph. Place my formula sheet. Okay. So as artificial elements are created, they're added to the periodic table. In 1982, the 109th element, unilenium, was created. It was found that unilenium-226 emits alpha particles as it decays. So I actually, first of all, I think that on your periodic table, element 109 actually has a proper name now. I'm just seeing if it's in the Science 24 one, because that's the only other. Oh, here it is. It's mite-nerium. Okay, so you can use this if you want, or you can use the unilenium, because it's going to be hard. Whoops, I did a capital M. We'll pretend that's a lowercase m. So I'm assuming this was named after some guy named Meitner. So that's usually what they name these after. Okay, and the symbol is MT, like mounting. Okay. So we'll use that instead of unilenium. So we want to write the decay equation. So for this is for mite-nerium 226. So 226, 109, mite-nerium. Brings out my nasal cold quite a bit. Okay, and we were told up here emits alpha particles as it decays. So it emits an alpha particle. So 4,2He, which means what we have left is 226 minus 4, so 222, and 109 minus 2, which is 107. And element 107 is borium. Ha. I'm boring you. Okay, it's a borium. I did the thing with the capital letter again there. Borium. B-O-H-R-I-U-M. So clearly named after Niels Bohr. Okay, so that's the decay equation. And then what is the half-life of unilenium, and how can you be sure? So half-life, so it starts, we've got milligrams, so it starts with 10 milligrams. So half is 5 milligrams. So what you do then is you draw a straight line across at 5, and then you pick off what your half-life is. So here it looks to be 3, oh, this is a bad scale, hey, with 3. So anyway, 3.33. Let's see, so 3 1/3 milliseconds. So that's the half-life. Then, how can you be sure? So what you want to do is check the second half-life. See if the second half-life is the same amount of time. And if 3 1/3 is the right one, or is a good estimate of the half-life, then your second half-life should be at 6 2/3. I'm just going to change my pen color here. Orange? No, that's red. Pink. Okay. So 2 1/2. Oh, okay. No, I didn't like that. I'm not sure what that was all about. I'll try to do something normal here then. Oh, I see, because it's broken. Yeah. Okay, well, let's just pick a blue then. So 2 1/2. Go across there. 2 1/2. So two half-lives from the graph is 6 2/3, which means it's a relatively decent estimate for that particular half-life. You guys are going to do a lab on Thursday where you're going to be all over the place, and it's not going to be as good of an estimate as it could be, but it also is more, this is a diploma question, right? So they do it sort of that It does have to actually kind of work out. But in reality, in a lab, there would be a great deal of probability involved in that. Okay, and that's decay rates. So let's see, it should be Tuesday night you guys are watching this, or Wednesday morning, depending on when you looked at it. We're going to spend all day Wednesday doing some questions and working together on them, because some of these questions can be a bit challenging. And then Thursday we'll do a lab. So I will see you then. Have a good night.